Imagine a temperature so cold that a solid, industrial grade steel I-beam just shatters like a cheap wine glass if you tap it with a hammer.
Yeah, it completely shatters.
Now, imagine relying on this really thin metal frame to hold back thousands of gallons of highly explosive, super chilled rocket fuel in that exact same temperature, all while hurtling through the vacuum of space.
It is genuinely hard to wrap your head around.
It really is. So welcome to the deep dive. If you are the kind of person who loves discovering the hidden, invisible architecture making the impossible possible, you are in exactly the right place.
We were looking at a material today that is literally hiding in plain sight, just doing a job that fundamentally defies our everyday logic.
Right. We have a stack of engineering notes and industry breakdowns here, specifically focusing on this paper titled Cryogenic Aluminium Sections, Engineering for Extreme Low Temperatures.
Yes, the cryogenic applications.
Exactly. So our mission today is to uncover how an everyday material, aluminium, is secretly serving as the highly engineered backbone for the most extreme freezing environments on Earth and obviously in outer space.
Which is wild when you think about it.
Totally. Okay, let's unpack this because, well, extreme cold doesn't quite capture the actual physics of what we were talking about here.
It really doesn't. To set the baseline here, when we talk about a cryogenic environment in engineering, we're operating below minus 150 degrees Celsius.
Minus 150 degrees.
Yeah. And at this low of a temperature, the physical rules of the game just completely change. Conventional materials undergo severe thermal stress.
Right.
They warp, their internal structures just lock up, and ultimately they fail catastrophically.
Yeah.
So our goal today is to look at exactly why highly engineered aluminum doesn't just survive these conditions, but actually thrives in them.
Minus 150 degrees Celsius. That is significantly colder than the lowest natural temperature ever recorded on Earth.
By a wide margin, yeah.
Right. So before we even get into how aluminium handles this, we really need to understand the mechanism of why standard materials fail. Because if you're listening to this and wondering, hey, why don't they just insulate steel better to keep it warm? The answer really comes down to what is happening at the atomic level.
Right, exactly. Because temperature, fundamentally, is just a measurement of atomic movement.
Right.
So when you drop down to minus 150 degrees, that atomic vibration just slows to an absolute crawl. And for most conventional structural metals, like your standard carbon steel, this is a fatal problem.
Because they lose their flexibility.
Precisely. They completely lose their ductility, which is their ability to flex or bend or deform under stress without breaking. Instead, they become severely, dangerously brittle.
It's like leaving a plastic food container in the freezer overnight.
Oh, that's a great example.
Right, you pull it out, and if you accidentally drop it on the kitchen floor, it doesn't just bounce and deform like it usually would at room temperature. It shatters into a million incredibly sharp pieces.
Yeah, exactly.
And that is exactly what is happening to normal structural metals. You apply a little mechanical pressure, or maybe there's a slight vibration, and cracked.
And in the industries we are talking about, a crack isn't just an inconvenience. It's a catastrophic hazard.
Yeah.
But this is where aluminium reveals its hidden superpower, and it all comes down to its crystal lattice structure.
The geometry of the atoms.
Right. So steel has what is called a body-centered cubic structure. When it gets cold, the atoms are arranged in a way that prevents the internal slip planes from moving. The metal literally cannot deform.
It just locks up completely.
Yeah. Aluminium, on the other hand, has a face-centered cubic structure.
Which means the geometry is completely different.
Exactly. Imagine stacking oranges in a crate.
Okay.
The face-centered cubic geometry of aluminium packs the atoms closely, but leaves multiple, highly symmetrical planes where layers of atoms can easily slide past one another.
Oh, I see.
So even when atomic vibration drops to near zero at minus 150 degrees, those planes can still slip. Because of that specific geometry, aluminium is the rare exception to the brittleness rule.
That is wild.
It retains its toughness and keeps its ductility as the temperature drops.
That is so counterintuitive. You generally assume that as things freeze, everything just becomes rigid and fragile.
Well, most things do. But aluminium also brings a few other critical thermodynamic properties to the table. Like, it has exceptional thermal conductivity, meaning it distributes extreme cold evenly across its surface.
Why does that matter so much?
Because if a material freezes in patches, you get localized contraction, which essentially tears the metal apart from the inside. Aluminium resists that. It maintains incredible dimensional stability.
What's fascinating to me in these sources is that it's not just about surviving the cold, it's about surviving the environment surrounding the cold.
What's fascinating here is that aluminium naturally forms this microscopic oxide layer, the absolute moment it is exposed to air.
So it's protecting itself.
Exactly. It provides natural corrosion resistance. And when you combine that with its low embrittlement, you are significantly reducing the maintenance weight, the likelihood of system failures.
Because you don't need all the extra protective layers.
Right. You don't need to coat cryogenic piping in heavy protective paints or, constantly replace rusted joints.
Which brings up a pretty big logistical friction point. If this environment is so demanding and failure is obviously not an option, why not use other advanced materials?
Like what?
Well, we hear about carbon fiber and space-age superalloys all the time. Surely a composite is better for aerospace or heavy industry than aluminium, right?
It's a completely logical assumption, but to answer it, we really have to evaluate the engineering rivals. Steel, titanium, and composites. We already discussed steel. It becomes a brittle liability.
Right. And even if you tried to heavily insulate the steel to keep it above that brittle threshold, the volume and the weight penalty of all that insulation just makes it useless for transport or aerospace. So we can scratch steel.
What about titanium? So titanium is remarkably strong, and it handles temperature well, but the raw material and the machining costs are just staggering.
Oh, just too expensive.
Exactly. If you are building massive infrastructure, say a miles-long cryogenic piping network, using titanium would bankrupt the project before ground was even broken.
Wow. Okay, so what about the modern composites like carbon fiber?
They are exceptionally lightweight and strong, yeah.
Yeah.
But they face this really critical thermodynamic flaw called delamination.
Because composites are literally made of different materials layered together.
Precisely. You have carbon fibers suspended in a polymer resin. So when you drop the temperature to minus 150 degrees, the carbon fiber and the resin contract at totally different rates.
Oh, that sounds like a mess.
It's like bonding a sheet of rubber to a sheet of glass and then freezing them. They pull against each other until the layers physically just tear apart. Aluminium hits this perfect, elusive balance. It is lightweight, exceptionally tough in the cold, thermally efficient, and structurally uniform.
Oh, wait, I want to clarify something here. We aren't talking about the exact same elemental material used to make a soda can being sent into deep space, right?
Not at all. And this raises an important question about how we manipulate basic elements to sort of cheat physics. We are talking about highly optimized alloys, specifically the 5XX and 6XX series.
The specific chemical recipe.
Yes, and it relies on a principle called solid solution strengthening. The 5XX series adds magnesium to the aluminium.
Okay, what does the magnesium do?
Because magnesium atoms are a slightly different size than aluminium atoms, they sit inside that face-centered cubic lattice we talked about and create just enough internal friction to dramatically increase the yield strength.
But without freezing those slip planes.
Exactly. It stays tough in the cold.
Wow. And the 6XX series.
The 6XX series adds both magnesium and silicon.
Ah.
This allows the metal to form microscopic magnesium silicide precipitates when it's heat treated. It essentially locks the internal structure for even greater mechanical load-bearing capacity.
So they're really tuning the metal.
Oh, absolutely. Engineers meticulously balance these alloy recipes based on the operating temperature, the internal pressure of the liquids, and the structural load, just to ensure long-term safety.
And the actual physical forming of these alloys is just as critical. I really want to highlight a manufacturing detail from the text here because these components aren't just poured into a cast or, welded together from flat sheets. They are extruded.
Yes, the extrusion process is where the theoretical physics actually becomes practical engineering.
For anyone visualizing this at home, extrusion is structurally similar to pushing Play-Doh through a plastic shape maker, but obviously scaled up to an immense industrial level.
Yeah, that's the perfect analogy.
You take this massive solid billet of heated aluminum alloy and use immense hydraulic pressure to just force it through a perfectly machined steel die.
And that physical mechanism is fundamentally superior to fabricating or welding.
Why is that?
Because when you weld pieces of metal together, you create a heat-affected zone. That seam is a natural structural weak point, and under severe thermal cycling, it is the absolute first place a crack will propagate.
Oh, that makes sense.
But extruded sections provide uniform, continuous material properties. The grain structure of the metal aligns perfectly in the direction of the extrusion.
It also allows for incredibly tight dimensional tolerances. The sources point out that the global supply chain for this precise engineering is just vast.
It really is.
Like top aluminum extrusion companies, including these massive manufacturing hubs based in Ahmedabad, India, are completely crucial to this ecosystem. They are producing highly customized, complex profiles that meet incredibly strict international cryogenic standards.
And the quality control required to certify these parts is staggering.
Yeah.
I mean, these manufacturers are executing strict mechanical destruction tests, precise chemical analysis of the magnesium and silicon ratios, and really aggressive thermal cycling tests.
Just to make sure it works in the cold.
Yeah, they have to guarantee that a specific batch will perform flawlessly when the temperature suddenly drops.
So if we have miles of this perfect, precision extruded, freeze-proof metal just rolling out of facilities, who is actually buying it?
So many industries.
Let's look at the macro-scale infrastructure relying on these extrusions right now, because the first sector that dominates the research is LNG, liquefied natural gas.
LNG perfectly illustrates why manipulating thermodynamics is so essential for modern logistics. You see, to transport natural gas efficiently across the oceans, you have to cool it down to minus 162 degrees Celsius.
Minus 100 to 62 degrees.
Yeah, and at that precise temperature, the gas condenses into a liquid and its volume shrinks to 1/600th of its original size.
Which completely rewrites the economics of global energy. I mean, you are fitting 600 times more fuel onto a single transport ship.
Exactly. But containing a liquid at minus 162 degrees on a constantly moving vessel in the middle of the ocean is just an engineering nightmare.
I can imagine.
Cryogenic aluminium sections are the skeletal framework for the enormous LNG storage tanks, the internal containment grids on the ships, the transfer piping networks, and the high-pressure valves.
And this is where that weight equation we talked about comes into play. If you build a massive storage tank out of an alloy that is even slightly heavier, the structural foundation of the facility has to be massively reinforced.
Exactly.
And the transport ships would sit lower in the water, creating more drag, which means they burn more fuel just to transport the payload.
It's a vicious cycle.
So the lightweight nature of aluminium radically simplifies installation and just slashes the lifecycle maintenance costs of the entire global energy network.
It acts as a massive economic multiplier.
That's right.
But, we shouldn't limit our perspective to heavy industry. The applications in the medical field highlight a completely different set of physical demands.
Yeah, the medical applications in the source material really shift the perspective. Because these cryogenic sections are non-negotiable for the ultra-low temperature storage of vaccines, blood supplies, and biological samples.
Right, the biobanks.
Exactly. When the goal is to preserve organic material for decades, temperature stability is a strict requirement. If the structural integrity of a storage vat fractures because of thermal stress, you don't just lose time, you lose life-saving medicine.
And beyond biological storage, there is this structural application in clinical diagnostics that relies on a very specific, rare trait of aluminium.
Oh, the MRI machines. This was such an aha moment in the text for me. This is where the physics of the material really shines.
It really is.
MRI stands for magnetic resonance imaging. And these machines operate using these superconducting magnets that have to be cooled by liquid helium.
Right.
And liquid helium brings the internal temperature to near absolute zero.
Which means the structural frame holding this incredibly sensitive freezing cold technology together has to handle the absolute extreme of cryogenic temperatures perfectly.
And it faces another problem, too.
Yeah, it faces a massive electromagnetic hurdle.
Right, because the magnetic field generated by an MRI is so immensely powerful, it can literally pull a steel oxygen tank across a room and smash it into the machine.
It's incredibly dangerous.
So if you attempt to build the cryogenic support frame out of steel, or really any ferromagnetic metal, the eddy currents and the sheer magnetic pull would literally tear the machine apart the second you turn it on.
Exactly. But aluminium, however, is paramagnetic. So in the context of an MRI machine, it is effectively non-magnetic.
It just doesn't react.
Right. It does not interfere with the magnetic resonance at all, and it survives the liquid helium temperatures thanks to that face-centered cubic lattice we mentioned. It serves as the perfect invisible structural support. Every single time someone lies down in that imaging tube, they are completely surrounded by highly engineered aluminum profiles.
And the sources note an additional clinical benefit that ties directly back to how the metal is manufactured, which is hygiene.
Oh, yes, the extrusion process.
Because these profiles are pushed through those advanced extrusion dies rather than welded together, the surface finish is completely uniform. There are no microscopic pits, no rough seams, or weld spatter where dangerous pathogens can hide.
It's totally smooth.
Exactly. It makes the material exceptionally easy to sterilize, which significantly reduces contamination risks in sterile medical environments.
It is remarkable continuity when you step back and look at it. From massive ships traversing the ocean with liquid gas to the most sterile, precise rooms in a hospital, it is the exact same metallurgical foundation solving the problem.
Let's push this engineering to its absolute limit, though, because from the constraints of earthbound infrastructure, the logical escalation is the ultimate extreme environment, outer space.
Space is where cryogenic engineering faces a uniquely violent set of variables. I mean, you are dealing with the absolute vacuum of space, ambient temperatures dropping near absolute zero, and the immense mechanical trauma of a rocket launch.
The sources outline how aluminium is essentially the structural backbone of space exploration. The lifeblood of modern spacecraft are cryogenic fuels, like liquid oxygen and liquid hydrogen.
Right.
And they have to be stored at mind-numbing temperatures inside the rocket right up until the exact microsecond of ignition.
And in aerospace, the fuel penalty equation dictates everything.
What do you mean by fuel penalty?
Every single gram of mass you add to a rocket's structure requires exponentially more fuel to lift it out of Earth's gravity well. This cascades, impacting the entire mission cost and severely limiting the payload capacity.
So every ounce counts.
Absolutely. Aluminium's exceptional strength-to-weight ratio allows the spacecraft to endure the severe thermal contraction of storing cryogenic fuels, the acoustic shock and vibrational stress of launch, and the harsh radiation of space exposure, all without adding excess mass.
And aerospace engineers use these extruded profiles for the skeletal frameworks of satellites, too. By machining a custom extrusion die, they can create incredibly complex geometric cross-sections, shapes that offer maximum stiffness and load-bearing capacity while just hollowing out any unnecessary material.
It's exactly like designing lightweight metal bones for a spacecraft. If we connect this to the bigger picture, the material science here isn't just about pushing the boundaries of deep space exploration. It is deeply intertwined with the sustainable future of our own planet. The text heavily emphasizes aluminium's role in a circular economy.
Which is a crucial detail because when an old satellite falls out of orbit or, an outdated LNG plant is decommissioned, those tons of metal don't just become industrial garbage.
Exactly. Aluminium is infinitely recyclable.
Infinitely.
Yeah. Unlike plastics or complex composite materials that degrade structurally every time they are melted down, aluminium maintains its exact original strength and chemical integrity upon reuse. Furthermore, recycling aluminium requires only about 5% of the energy needed to produce virgin metal from raw bauxite ore.
And that recycled material is actively building green tech right now.
Yes, it is.
The sources highlight that the precise extrusion technology utilized for cryogenic sections is also deployed to manufacture the robust frames and mounting structures for massive commercial solar panel arrays.
Which face their own extremes.
Right. These structures have to withstand decades of brutal UV exposure, high winds, and severe thermal cycling. I mean, from freezing desert nights to scorching midday heat, and they have to do it without degrading or losing their shape.
It creates this really elegant technological loop. The foundational material securing our renewable energy infrastructure on Earth is the exact same material enabling our deep space exploration.
Here's where it gets really interesting, though, what comes next. Because the engineering demands never stop.
No, they don't.
The sources map out several accelerating future trends for cryogenic aluminium.
The global demand is poised to skyrocket, particularly when you look at the shift toward a hydrogen economy.
Hydrogen needs to be even colder, right?
Much colder. Liquid hydrogen requires even lower temperatures than LNG. It must be cooled to minus 253 degrees Celsius. That is barely 20 degrees above absolute zero. So as we build out a global infrastructure for hydrogen fuel cells and heavy transportation and industrial power, the requirement for flawless, highly ductile cryogenic sections will just scale immensely.
And the biotech sector is expanding at a similar rate. As we move toward more personalized medicine and massive long-term biological storage banks, the need for precise, sterile, cold temperature infrastructure just grows right alongside it.
And what engineers are currently developing is the integration of these aluminum sections with advanced insulation materials and smart monitoring systems.
Smart systems, like digital.
Yeah. Imagine extruded aluminum pipes that don't merely contain the cryogenic liquid, but feature microscopic sensors embedded directly into the metal profile.
Oh, that's incredible.
These sensors can monitor thermal stress, internal pressure, and structural integrity in real time, feeding telemetry back to a central hub. It is the literal marriage of advanced metallurgy and the Internet of Things.
So what does this all mean for you? We've traced the journey of a single, highly engineered material today. We looked at the specific geometric arrangement of atoms, allowing an alloy to remain tough at minus 150 degrees.
And colder.
Right, and colder. We followed those extruded shapes into the massive ships securing our global energy grid, into the MRI machines diagnosing our injuries without tearing themselves apart, all the way to the rockets pushing our species into the stars.
It is a really powerful reminder that the most critical technologies in our modern world rely entirely on materials that do their jobs silently, reliably, and perfectly under the most extreme conditions imaginable.
The next time you walk past an MRI room in a hospital, or see a news report about a liquid natural gas terminal, or watch a rocket launch stream on your phone, don't just look at the massive scale of the technology or the fire from the engine.
Take a closer look.
Yeah, take a second to think about the hidden, highly engineered, freezing cold aluminium framework that is making it all physically possible. It really is the invisible skeleton of the modern world.
And it leaves you with something to consider, really. If a material as commonplace as aluminium, something we interact with in our kitchens and cars daily, has these hidden extreme capabilities just waiting to be unlocked by precision engineering and a deep understanding of atomic structure, it makes you wonder,
It definitely does.
what other everyday materials sitting in your home right now are hiding superpowers that might define the next century of space or medical technology?
That is exactly why we do this show. Thank you for joining us on this deep dive. Keep questioning the incredible hidden systems built into the world around you, and we will catch you next time.